Good day. For those of you who do not know us, we're the instructional staff for ECE 150. Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to describe Bitwise and Bitshift operators. In this presentation, we will introduce bitwise logical operators and contrast these with the Boolean logical operators we have already seen. We will describe the bitwise exclusive OR operator in addition to the bitwise and bitwise OR operators. We will also introduce and describe the unary bitwise NOT or complement operator. Finally, we will describe both the left and right shift operators. All right, we've already seen two logical operators. They were the binary logical AND operator and the binary logical OR operator. And of course, their behavior was defined by the values of the operands. So the AND of x and y is true if and only if both x and y are true, whereas the OR of x and y is true if either x or y is true. Recall that any zero value is considered to be false in C++, while any non-zero value is considered to be true. Now, true and false themselves have values of 1 and 0 respectively, but 7 is as true is. Now, recall that the primitive integer data types we've been looking at have a fixed number of bits. For example, int has 32 bits. Now, given any 2 bits in 2 different integers, could we not define a bitwise AND or a bitwise OR of those 2 bit values where 0 is false and 1 is true? And so if 2 bits were both 1, then the AND of those 2 bits would also be 1. Now, there are 3 binary bitwise operators in C++. Basically, what happens here, each of these operators will compare pairwise each of the bits in the 2 operands. And the first one we're going to look at is the bitwise AND operator, which compares each pair of corresponding bits and performs an AND operation on those bits. Each result is 1 if and only if both bits are also 1. So here we see 2 numbers in binary. And if we perform a bitwise AND on each of them, then the result is 1 if and only if both operands have a 1 in the corresponding location. On the other hand, in each of these 6 locations, we notice that either only one of the 2 operands has a 1 in a location, or neither does. So the bitwise AND of these last 6 bits is 0. All right, let's take a look at a program that uses the bitwise AND operator. And as before with arithmetic operations, a binary bitwise operator does not change the values of the operands. It simply performs a calculation based on those operands. So here we have a program that initializes 2 local variables of type unsigned int with numbers in binary. We then print those 2 numbers out, which will be printed in decimal, and then we print out the result of the bitwise AND of both m and n. All right, so here's what the output looks like. Well, you can't really understand anything here because there's no real way to comprehend or understand how the 2 are related when the results are in decimal. But if we print or convert the result, which is 11,094,592, to binary, we can see that yes, indeed, the result is the bitwise AND of the two operands. The second bitwise operator we're going to look at is the bitwise OR operator, which uses a single pipe, just like the bitwise AND used a single ampersand. Recall that the logical OR operator was a double pipe. So, given any two operands of the same type, a logical OR is applied to the corresponding pairs of bits. Each result is 0 if and only if both bits are 0. Otherwise, at least one of the bits is 1, in which case the result will also be 1. So here are two 32-bit integers, and we note that if both corresponding bits are 0, then in the result we also see that bit set to 0. On the other hand, if one or both of the operands have a bit set to 1, then the result of the bitwise OR operation in those corresponding bits is also 1. Again, here we see a program that assigns two values to local variables m and n, and then prints out the values m and n as well as the bitwise OR of those two local variables. Here's the output, and if we convert the output to binary, we note that yes, indeed, this is the bitwise OR of both m and n. You can compare this on your own time if you wish. The third bitwise operator is the exclusive OR operator, or XOR operator. This has no equivalent binary logical operator. So for a result for the exclusive OR to be true, one but not both operands must be true. So unlike OR, which is true if either of the operands are true, the XOR operation is true only if one of the operands has a value of 1 in a particular location. So 0 XOR 0 is 0, 1 XOR 1 is 0, and only if one of the bits is 1 is the XOR equal to 1. So the bitwise OR operator is represented by a caret, which you may have thought was the exponentiation operator. However, it's in fact the bitwise OR operator, bitwise XOR operator. There is no equivalent binary logical operator. There is no double caret operator in C++. So if both bits have the same value, the result is 0, otherwise it is equal to 1. So here we see two 32-bit integers, and we are calculating the XOR of each of the bits. So for example, in these 3 bits, only one of the operands has a value of 1, so the XOR of these 3 is 1. On the other hand, in each of these 6 locations, both operands have the same value, either 0 or 1, in which case the XOR is 0. And once again, here is a program that prints out the result of the XOR operation. And so if we were to execute this program, this would be the output, and if we converted the output to binary, we would see that yes, indeed, that is the exclusive OR operation applied bitwise to each of the operands. Now, as with the arithmetic operators, there are also automatic assignment operators for each of the three bitwise operators. So again, if you wanted to XOR C with 2, you can just use the notation C XOR equals 2, and the same for bitwise and bitwise OR as well. It's important to remember that there are no automatic assignment operators for the Boolean logical operators. So there is no double ampersand equals or double pipe equals in C++. There is a unary bitwise operator that is called the NOT operator or the complement operator. Basically, it is equivalent to applying a logical NOT to each bit within the data type. So, for example, given the number above, if we applied the unary NOT operator, then every single bit is flipped. So here's an example. Here we have a local variable m, and we print to the screen the bitwise NOT or complement of that local variable. As it is an int, all 32 bits will be flipped in their value. Now, here we see both m and not m. If you add these two together, what should you get? Think about it. Now, if you convert the second entry to binary, you will see that every single bit is indeed flipped to the opposite value. Now, you may be wondering, what is the significance of taking a bitwise operation with two different integers? Well, what this is actually useful for is the manipulation of the individual bits in a number. So rather than adding or subtracting, we're now going to be able to access and manipulate the individual bits of a number. So, suppose here we have this local variable. I'm calling it mask. It has a value of 256. 256 is 2 to the 8. Now, as you will remember, the rightmost bit is considered to be bit 0. And 256 indicates that bit 8 is the one that is set to 1. Any single power of 2 has only one bit that is set to 1, with all other bits set to 0. If a number is not a power of 2, at least 2 different entries or 2 different bits will be 1. Unless, of course, it's 0, in which case none of them are 1. But that's just a special case. Now, suppose n is any unsigned integer value. In this case, I'm just asking the user to give me a value of n. We can set the 8th bit of this integer, unsigned integer n, to 1 by simply doing an automatic bitwise OR with this mask. So that will set bit number 8 to the value 1. All other bits of the integer n are left unchanged. Alternatively, I can set the 8th bit of n to 0. So I'm doing an automatic assignment of the bitwise operator AND with the complement of the mask. So what does this do? Well, the 8th bit is 1. Now, if we do a complement, then all the bits will be 1 except for the 8th bit. So if I now do a bitwise AND of n with all ones everywhere except in the 8th bit, then all other bits will be left unchanged, but anything and 0, which is now in the 8th location of not mask, must be set to 0. So this sets the 8th bit of n to 0. You can use XOR to flip the bit value between 0 and 1. So in this case, if n originally had an 8th bit that was equal to 1, after applying XOR with this mask, then the 8th bit will be 0. Did I get that right? It's going to be flipped. So if it was originally 1, it becomes 0. If it's originally 0, it becomes 1. Notice that all other bits are left unchanged because 0 XOR 0 is 0 and 0 XOR 1 is 1. Finally, we can perform a task if and only if the 8th bit is set to 1 by using this command here. So if n and bitwise AND mask, well, this will only be true or non-zero if the nth bit is 1. So n bitwise AND mask is a nice test that allows us to perform something if and only if that 8th bit is set to 1 in n. Let's take a look at this program. Here I have defined 4 local variables of type unsigned short with the values 1, 2, 4, and 8. These being powers of 2 means that each of them has exactly 1 bit set to 1, specifically bit 0, then bit 1, then bit 2, and mask 3 has bit 3 set to 1. Suppose we ask the user for an integer and the user enters the value 14. Well, now n stores this value in binary as 14 is equal to 8 plus 4 plus 2. Now, suppose we execute the command n bitwise OR equals mask 0. Well, mask 0 has a 1 at bit 0, and so what this will do is it will set bit 0 to 1 regardless of what value was there previously. In this case, bit 0 was 0, and so it will be set to 1. If bit 1 was, or bit 0 was already 1, this would have no effect. It would remain as 1. Next, suppose we do a bitwise AND equals with the complement of mask 1. This has the effect of setting bit 1 to 0 regardless of what value was previously stored there. Now in this case, bit 1 is equal to 1, so after executing this statement, bit 1 will be set to 0. Next, we do a bitwise XOR equals with mask 2, and that has bit 2 set to 1, and so this statement will flip the value of bit 2. Now in this case, bit 2, being the third from the right, is set to 1, so if this command was executed, it would set bit 2 to 0. If bit 2 was originally 0, this statement would then set it to 1. Finally, I have a conditional statement. If n bitwise AND with mask 3, I will print the statement bit 3 is set to 1, otherwise I will print the statement bit 3 is set to 0. Well, in this case, bit 3 is indeed 1, and so therefore the condition is true, and bit 3 is 1, will be printed to the console output. All right, so we've finished introducing the bitwise operators, and now we're going to look at two operators that are very closely related to the bitwise operators, and these are the Bitshift operators. And what these two operators do is just move the bits inside a primitive data type, either left or right. The first is the left shift operator, and it's represented by two less than symbols. You can see that it suggests that the bits are being moved to the left based on the direction the less than symbols point. So in this example, the operand OP has the initial value 17, and if I initialize the local variable Q1 with OP left shifted n bits, then the bits inside OP are moved n bits to the left. N must be a non-negative integer. The right shift operator does the same, except it moves the bits to the right. And once again, n must be a non-negative integer. A left shift of -3 bits is not a right shift of 3 bits. Now, any bits shifted beyond the last position within the memory allocated for that local variable are just lost. So, for example, if the operand was 4 bytes in size, say an unsigned int, and has the value we see here, then if we were to right shift this by 5, then all the bits would be moved over by 5, and 5 zeros would be introduced at the left hand side. You'll notice that we lost 2 bits that were set to 1 at the right. If we move this same operand over by 12, again, all the bits would be shifted over by 12, and the last 12 bits on the right would be lost. On the other hand, if we shifted to the left 8 bits on the left would be lost. The remaining bits would be shifted to the left by 8, and the last 8 bits would now be 0. And if we left shifted by 13, a similar result would occur. Now, there are two automatic bit shift operators as well, as you may expect. OP left shift equals n would shift the bits of OP by n bits. Similarly, OP right shifted equals n would shift the bits of OP by n bits. N must be a positive integer. Now, bit shift operators can be used to precisely read and or place bits within an integer or other primitive data type. We're going to look at an example that uses bit shifting and bitwise AND to print a number to the screen in binary. Here's a nice little program where we query the user to enter a positive integer. Suppose the user enters the value 999,999,999. Easy enough. Now here, k is initialized with the value 1 left shifted by 31. Now k is an unsigned integer, so it occupies 4 bytes or 32 bits. With 32 bits, 1 is all zeros except for a 1 in the rightmost bit. But now, if I left shift that 1, I move that 1 bit to the left 31 times, it now ends up in the most significant bit position, or here, as you can see, in bit number 31, which is the leftmost bit. Now, when I perform a bitwise AND with this value and n, This is non-zero if the 31st bit of n is 1 and it's 0 otherwise. So if the 31st bit of n is 1, we will print out a 1, otherwise we will print a 0. Alright, when the loop is over, we will then perform an automatic assignment of right shift equals 1 with the local looping variable k, and what this will do is it will move that 1 bit to the right by 1. We execute the loop of the body again, and now we check if that bit of n is 1, and we print out a 1 or 0 as is appropriate. We loop again. At the end of the loop, we right shift again and again, and we keep on doing this until very soon the 1 has been right shifted to the last location. Now, when we now do the loop body, we will check if the 0th bit of k is 1 and print out the appropriate number. Then finally, when we right shift k by 1 more bit, k becomes 0, and so the loop stops. If n was initially given as 999,999,999, this would print to the screen this sequence of 1s and 0s. Okay, let's now review the operators we have seen so far. For arithmetic operators, we have 5 binary operators, plus, minus, times, divide, and modulo, and 2 unary operators, the neutral and the negation operator. There are 6 comparison operators that are binary. There are 2 binary logical operators and 1 unary logical operator, being and, or, and not. There are 3 bitwise operators that include and, or, and XOR, and the complement operator, or the bitwise not operator. We've just finished looking at the Bitshift operators, shifting bits both to the left and to the right, and we've also been using the assignment operator. Additionally, for almost all of these operators that are binary, there are also corresponding automatic assignment operators, with the notable exception of the logical binary operators. So, after this topic, you are now aware of bitwise and bit shifting operators. You understand how these operators work, and you understand that there are automatic operators corresponding to each of these binary operators. Also, there are no automatic assignment operators for logical and or logical or. Here are the references, the colophon, and a disclaimer. Cheers!